Welcome to SSI Meetup. Today we'll be talking about machine identity with Mrinal Wadhwa. And the idea is that identity goes beyond organizations or people. It also extends to machines or the Internet of Things. And in the future, we will also cover other things like pets and animals, but how identity extends to that world. But today we'll be talking about identity for machines and the Internet of Things. And I've been exchanging messages with Mrinal for 4 or 5 months now. So I'm really happy that he accepted this invitation today. He has an amazing slide deck to share with us. Just going to review very quickly with you in slide number 2 what SSI Meetup is about and why we're doing this whole thing for you. So the reason for SSI Meetup to exist is because we want to empower global SSI communities. And this is open to everyone, to individuals, to companies, to associations, to anyone who wants to participate. And we share all the content from our guests with the Creative Commons by share alike license, which basically means that you can reuse this content afterwards. Once we publish it in Google Slides or SlideShare or the video, you can reuse it, and hopefully you will create physical meetups around the world in your community, in your city, in your country, where you will explain what SSI is about, how it works, and make this whole thing grow. And the only thing you have to do is to credit back the author of the material. Today, this is Mrinal with his company, and also credit back SSI Meetup as a source where you found this material, and that's it. And then you have the whole super cool slides that all our guests so far have been creating, and I think today we are already in webinar number 25. If you have any questions during the presentation, please just interrupt at any point of time. You have a questions tool that you can use, and I'll be sharing those questions with Mrinal, or you can also ask at the end of the whole session. And I think, yes, that covers all the main points. And Mrinal, thank you so much, and very welcome to SSI Meetup, and it's a pleasure to have you with us here today.
Thank you, Alex. It's an absolute pleasure to be here. I want to thank everyone in the SSI community for joining, and also for all the great contributions that folks in W3C and DIF and other organizations have been making to the community. So I'm excited about this. Thank you, everyone, for joining. So a little bit about sort of me. I'm CTO at Ockam, and Ockam is a open source toolchain for building secure, trustworthy, reliable IoT systems. And during the slide deck, I'll touch a little bit on how we're approaching those problems. So I'm personally passionate about building systems where connected machines come together with intelligent algorithms to improve our lives, right? Almost like magic. And over the years, I've had the opportunity to be involved in the design of multiple such systems. For example, devices and algorithms that were installed in a very large plum farm, one of the largest in the world, trying to reduce wastage of water and improve yields of the farm. Similarly, systems that were installed in city downtowns in multiple North American cities to reduce traffic congestion and pollution. And similarly, systems in a major coastal city to do flood warning and emergency response. So those were interesting projects. However, most of my days were spent what I can best describe as doing what I can best describe as digital plumbing. So let me illustrate that with an example. So let's take this really simple autonomous system. If a person enters a room, change room temperature to their preference. Seems simple enough. We should be able to build this. So let's think about how we may build this. And the moment you do that, you start running into a few basic questions. So for example, how do we identify a person? How do we authenticate them? How do we know they entered the room? Maybe with a device, but how do we identify the device? How do we authenticate the device? Can we trust that device? Room, similarly, how do we identify a room? how do we know which people are authorized to change a room's temperature? Change, how do we change the temperature of the room? Once again, maybe with a device, but how do we identify the device, authenticate it, trust it, etc.? Room temperature, once again, the definition of room temperature itself may be up for debates. Well, what is room temperature? Is it called temp in the system? Is it called temperature? Is it called T? What unit is it set in, etc.? And then finally, well, how do we even know what this particular person prefers? What exact temperature? And once again, definition of temperature is up for debate. So it gets rather complicated pretty quickly, even in this very simple scenario. What's worse is that a lot of times when you build such a system, it ends up being very, very tightly coupled with the components of that system. So to illustrate, I did a quick Google search to see if somebody else had already built such a system, and maybe I could just use their tool and not build it myself. And I found one on if this then that, and they'd written one specifically for the Nest thermostat, and if I had a Nest thermostat, it would work. But I don't have a Nest thermostat. I have a completely different device, and my business requirements may be different. Maybe I can't use a site like IFTTT. I need to use an enterprise product, and I need to do access control, etc. So the problem you very quickly run into is all of these identities and these preferences are locked in data silos. So person identity is locked up in thousands of people identity systems, all the way from Google, Facebook to enterprise Active Directory. Similarly, sensing entry, all phones and RFID sensors and other sensors all have different mechanisms, and their way of operating is different, and their way of controlling them is different, and their access to them is again locked up in hundreds or thousands of different systems. Similarly, identity of the room, preferences, changing with devices, once again, has similar problems. So you end up with this, n squared integration problem, which is very, very hard to solve. This is what I mean by I spend most of my days doing what I can best describe as digital plumbing. And sometimes, once in a while, there's some magic and you build something useful. So what's even more interesting is that all of these challenges in plumbing, all of that complexity, it manifests as other drawbacks. It manifests as weaknesses in a lot of these connected systems. They don't scale very well. They're not very secure. If you've seen the news in the past couple of years, you know how bad IoT security is these days. They're not really very private. And because of all of those reasons, they aren't trustworthy. They aren't reliable, right? So we can't build higher level systems on top of them because the foundation of source data and control instructions itself is weak. I think that a lot of the work that the SSI community and the W3C community have been doing over the last few years is very, very interesting in terms of solving some of these plumbing challenges and these architectural challenges. And I've noted a few of the building blocks that the community has worked on. And the rest of my talk is about how these building blocks make sense in the realm of connected devices and IoT systems, or even higher level systems, which are more autonomous and driven by algorithms. So let's start with decentralized identifiers. So decentralized identifiers, many of the questions in my earlier very simple autonomous system example were around establishing and proving identity of a device or a person or a room, right? And decentralized identifiers, I think, are a very elegant solution for all of those those identity challenges. And they tend to have this structure of a scheme, a method, and then a unique string that is unique within the scope of that method. In this particular example, the method here is the Ockam method, but you can imagine it could be the sovereign method or the uport method, or several of the other methods that the community is developing. But we're building this Ockam method that's trying to optimize and do things specifically for devices. So here's how a device sort of comes into existence. It generates a cryptographic key pair. It generates a DID from that cryptographic key pair, makes up what's called a DID document, signs that document with this new key pair, and then sends the data over to, in this case, the Ockam blockchain network, and the data then gets stored in the network. So what this is essentially a process of registering a DID, and the process can vary from method to method. But the end result is, if you have a sufficiently decentralized blockchain network, you guarantee that the registry entry is persistent and not modifiable by any one party. And this has some very interesting implications, I think. So first implication that you get out of this design of DIDs is that DIDs are globally resolvable, which means that if you have a DID string, you can resolve it to its DID document via its method. And in the past, if you look at old identity systems like UUIDs, etc., you didn't have this resolvability across systems capability. And this capability is very, very interesting because it breaks those silos. It breaks the identity silos where a lot of this data is locked up. And so, for example, Ockham's building a device identity and a device data system, and Sovereign's building a people identity system. And these two systems and the entities in these two systems can interoperate because of this common DID resolvability capability. So, for example, you can imagine an access control algorithm where the person identity lives in Sovereign, and the device that's actually giving control to, let's say, a room lives in Ockam. And these two things can interoperate in very interesting ways. And we'll get into that in a little more as we go further into the deck. But essentially, what blockchains do here is they enable globally resolvable yet decentralized namespace, right? So you've got this unique global namespace, and you can have IDs that are unique to each entity in that namespace across systems, which is very, very interesting, I think. So DID documents, so this is the document that you get back once you resolve a DID from its method. And the structure of this document is also very, very interesting. It primarily contains the DID itself, but then it contains a collection of public keys that represent public keys that are the corresponding private keys are assumed to be in possession of whoever is in control of this DID. And they can prove that possession using various authentication mechanisms. And there's also this service attribute, which we'll get into in a little bit as well. But this DID document is a linked data document, and it contains the public keys of that DID. This is an incredibly flexible scheme, because what that means is that once this document is stored on a blockchain, you can rotate and revoke keys without affecting the identity itself, right? So let's get into that in a second as well. So the first impact you get out of this mechanism is that these identities become cryptographically provable. So if you possess the corresponding private key to a public key, you can prove ownership of that identity via whatever authentication scheme is specified in the document. So that's interesting because older ID schemes, especially in the IoT realm, these ID schemes are, MAC addresses or IP addresses, and those addresses aren't provable cryptographically. So they're very, very easy to spoof, which is what happens in a very large number of device systems that have no cryptographic protections. So what ends up happening is somebody just flips a bit in your message and can pretend to be a completely different device. What's also interesting about this is that even if you were using sort of traditional cryptography and you assigned public-private key pairs to all of these devices, and you said, okay, maybe I could just use the public key as the identity itself. The problem with that approach is that that creates tight coupling with a specific public key. And so you can't rotate that public key, and that creates a very brittle trust model. It also creates tight coupling with the cryptographic algorithms of that specific public key. And what I like about the design of DID documents is that they're flexible in terms of which key algorithms and which signature algorithms you use. And you can define your own as new hardware comes into the market, etc. So different devices will have different cryptographic abilities, and DID documents seem to be sort of future-proof to that, which is incredibly interesting as well from an IoT perspective. And finally, before I move on to the next sort of subject, this authentication scheme can be arbitrarily complex. It can be one signature, it can be multiple signatures from multiple parties, which also has some interesting implications in the IoT realm that I'll get into as we start talking about software updates. So, okay, DIDs are cryptographically provable. Another thing DIDs enable is sort of decentralized key management. And this is incredibly interesting for device-driven systems. So essentially, if you take a very simplified view of most IoT systems, there are devices on one end, and there's a back end on another end. And typically, you're receiving sensed data and acknowledgement from devices to the back end, and the back end sending over control instructions, firmware updates, configuration updates, etc. And you end up managing. If you want to build a secure system, you must assign each device a unique cryptographic key pair. The backend knows the public part of that key pair. The device knows the secret part. And you must assign the backend itself a cryptographic key pair. Only the backend has the secret, but all the devices have the public keys. And this, at large scale, when you're doing very large number of devices and you're producing them in some factory in China, let's say, you hit logistical challenges in managing these keys across a large number of devices. And that's part of the reason a lot of device companies end up not doing it, or making stupid mistakes like giving the same credentials to all devices. Which we've seen, for example, in the Mirai botnet case, where 600,000 devices had, some variation of 60 passwords. So what's nice about DIDs and the decentralized key management that's enabled by it is that, starting from the very first step, when you're registering a new device to a blockchain, you don't get issued an identity from some central certificate authority. You can just generate your own identity and you can register it with the corresponding blockchain. What's nice about this is that it eliminates complexity in the process of having a hierarchy of certificate authorities, some of which must live in that manufacturing facility in China or must have an API endpoint in that manufacturing facility. And so it exposes your certificate authority to compromise in terms of, somebody may issue malicious certificates, or steal the private keys of the certificate authority itself. So compared to that's old scheme of centralized PKI hierarchies, this new scheme of just generate your ID and register it is much more flexible and much more robust, in my opinion, because it eliminates that complexity of managing across tens of manufacturing facilities how you provision cryptographic keys into devices. The other side of this equation, which is provisioning public keys of the backends into devices, is also very interesting. So if you, instead of provisioning a public key into a device, if you were to provision the DID of the backend service into a device, then you gain a lot of flexibility in terms of rotating and revoking the credentials that are private to the backend. So if you make the mistake of just hard coding a public key into the hardware of your device, for example, to do things like verified boot or signed firmware updates, then for example, let's say something like what happened to Asus a few days ago under the Shadow Hammer compromise that they've experienced a few days ago. Essentially, what's happened is somebody's managed to steal the private keys from a software update server at Asus, which is a big laptop manufacturer. And so now what that means is, because their public keys are hard-coded into devices, they have no mechanism of regaining control and reestablishing trust in those devices, because they can't deliver, they can't revoke those compromised credentials because they're hard-coded into the hardware of the device. Instead of hard-coding public keys, hard-coding a DID makes a lot more sense, because you eliminate that single point of failure private key. You can do lots of mechanisms around rotating those keys, revoking them. You can even have a protocol where private keys of the backend server are rotated once a week or once a month. What's also interesting is that going back to the DID document, because authentication schemes can be arbitrarily complex, you could imagine that there can be multi-signature authentication teams required to sign and update as a backend service, and that can add more robustness to the architecture as well. So, all right, so the decentralized key management aspect of DID design is also incredibly interesting. The last part of the DID document that I'll talk about is this, the service section, and this is incredibly powerful for devices as well. So devices have to do service discovery all the time. So, device gets manufactured in a factory and then gets shipped over to an install location. And when it turns on, it needs to know where to go, where's the endpoint that I need to go talk to. And this endpoint may not be known when the device is actually manufactured. And having this discovery element baked into the DID document has some interesting implications, because you could imagine that there's a manufacturer DID, and then maybe there's some shared relationship between this service element and the manufacturer's endpoint, or something like that. So you can imagine sort of zero-touch onboarding schemes that leverage this service endpoint in interesting ways. So this service endpoint could be used for, things like my example here, like how do I send a message to this device, or where's my software update service, or where's my where's my device onboarding service, or it could be used to describe the semantically describe the API of a device. So if there's an API that's available on the internet to interact with the device, you could describe that endpoint with metadata using various sort of semantic or schema-driven languages as well. So this is incredibly interesting, going back to my original problem, because this is another mechanism to eliminate the friction that you have to deal with as you bring on, thousands or millions of devices. It takes away a lot of that onboarding time. And so you can have zero-touch automated onboarding schemes, and you can have discovery across systems and across device infrastructures, which is incredibly interesting. So, okay, and I briefly hinted at this. The other point that I think, the other sort of effort that I think is very interesting that the web community has been working on for a couple of decades now, I think, is this notion of semantic data and linked data. And DID documents, as we all know, are also linked data document described in JSON LD, which is one of the linked data formats. But the broader idea of semantic linked data is very interesting to IoT systems as well, because we can bring semantic meaning and relationships to IoT data. So for example, instead of describing temperature as this arbitrary string called temperature, I could have chosen temp, I could have chosen T, or something else in my sort of my local language. It becomes very difficult for another party to understand what this means without actually talking to me and manually integrating with my system. If instead I were to describe the data with well-defined semantics, like for example using this schema called iotschema.org, then this reading has very specific meaning. It has specific units. It has specific context. So what this enables is that two developers who've never coordinated can independently build a temperature sensor and a temperature controller that would just magically work together. And this is not a new idea, right? So this capability has existed going back decades. But what's new is that before you got to this point, you had to deal with the identity challenges. And by having an identity scheme that also relies on linked data and then has a service discovery element, which could discover metadata about the API that you need to communicate with a device, you've now connected all the dots needed to create almost automatic integration between a lot of devices and device types and systems. So that part is interesting. Another thing that's interesting about linked data in general is that they can describe relationships, right? So this is property of says this not only is this a temperature reading, it's a temperature reading about a specific DID, which happens to be the DID of a specific room. And so you can describe these relationships, and you can create a relationship graph that isn't siloed inside one system. It spans several systems. And that's the part that's very, very interesting about DIDs. Because they're globally resolvable, this ID of a room could live in the Ockam system, but the ID of the person who's allowed to enter this room or who's allowed to read this temperature reading could live in a different system. For example, Sovereign or Uport, etc. So that's the part that's very, very interesting. So you can imagine this massive global entity relationship graph that algorithms and systems can reason about and leverage as a knowledge graph. And another sort of very interesting piece of work that's happening within the SSI community is verifiable claims or verifiable credentials. And they generally take this form, right? There's a subject, which is described with a DID. There's a property, and then there's a value of that property. But this claim, which is about the subject, about a property of the subject, is signed by an issuer. And that part is very interesting as well, right? So, for example, you could have, okay, this room has this exact temperature, but it's signed by a device, and it's signed by the private key of a device. So the data then becomes attributable to a specific device that has cryptographically signed this claim as the issuer of this claim. And this is what claims look like. This is specifically an example from Ockam. But once again, as we've seen, these claims can sort of span lots of systems. So this gives us a foundation to create signed, attributable, verifiable data from devices. And this is also not new. You could always just program a private key into a device and sign the data, but all the logistical challenges that are eliminated by the design of DIDs and DID documents, the decentralization that's enabled with storing DID documents in a blockchain, and then the flexibility of the design of DID documents leading up to the flexibility in the design of verifiable claims itself is what's interesting, right? So all of these pieces put together start to shape a very interesting set of possibilities. So this is just a flow of how signed data is created inside Ockam. And once again, we have specific support for specific hardware cryptography. Essentially, the sensor takes a, let's say some kind of sort of observation, could be temperature, could be vibration or something like that. And then it signs that claim and stores that claim inside Occam's blockchain. So this data then, once it enters the Occam blockchain, becomes attributable to this source forever. But there's no requirement that these claims must land in a blockchain. They can be exchanged privately as well, and I'll discuss that as we go further. But essentially, what all of this enables is a new kind of trust model, right? And it's kind of the old new. The PGP folks have followed this trust model for a very long time. But on the web, the more common trust model was this hierarchical X509 PKI trust model. And the problem with that model is that it is incredibly brittle, and it's prone to single points of failure. Case in point, the ASUS example I quoted earlier. But what's nice about the web of trust model is that instead of inheriting trust in a device because some central root authority signed an intermediate certificate, and then the intermediate certificate signed another intermediate certificate, and then that certificate finally issued this device a credential or a key pair, instead of that being a hierarchical trust model, the device just generates its own key pair, registers itself to a blockchain, and then other parties can make claims about the device that are signed by those parties. And you can assemble a collection of these claims, and what you get is a web of trust, a web of signed attributable information about a specific device. And you can use that to reason about the trustworthiness of a device at a particular instant in time. So you can ask questions where you say, okay, was this device made by a reputable manufacturer? Does the device have hardware based on, hardware-based cryptography and secure key storage? Does the device have a unique identity, cryptographic keys? Has the device been audited? Was the audit proof signed, or is just somebody sending in, making a web claim that they audited this? Are there known vulnerabilities? Was there a known vulnerability discovered yesterday? If so, the trustworthiness of that device today is less than it was day before yesterday. Does the device produce signed data? Can our firmware updates sign? So, is there a possibility that the firmware in the device is actually not what we think it is and is malicious? Does it have the latest firmware? Who installed the device? Who provisioned the device? All of these things about the life of a device become provable. And they don't have to be provable in public. You could imagine that some of this data stays private. In Ockam, we have this notion of private zones that are related to public hubs. But essentially, you can have systems where some information is private, but you can reveal proofs about that private information to the public. So a manufacturer may not reveal their entire manufacturing history, but they could reveal a proof that this specific device, a zero knowledge proof, essentially saying this specific device was audited by a trusted party, or it does have a secure element in it, right? Those kinds of proofs become feasible. And then some of the data can be public as well, and that can be used by the broader public to reason about the trustworthiness of the device. So, okay, so this auditable signed history of a device that no one party can manipulate becomes the foundation of trust in data from that device. And similarly, trust in, if the device is a controller, trust in the fact that it will control what you want it to control. So algorithms and protocols can leverage this globally resolvable, cryptographically provable identity of a device, along with cryptographically attributable claims about a device to reason about its trustworthiness in real time. And all of this put together is new and incredibly interesting. So for instance, right, you can imagine as a first step towards establishing trust, the DIF community has done some interesting work around DID auth, and this is Ockham's design on top of that work, and we're showing in this scenario how would how would a device authenticate with a backend service using when all you know is the DID of the backend service. So this is the scenario of, let's say, a software update service, and the device in its hardware has the public DID of the software update burnt or fused into the hardware, saying, okay, only boot if you get a software update signed by this DID. So the device, can go through this whole protocol of auth encryption and can arrive as a result with a mutually authenticated channel where the device knows that it is currently talking to that specific service identified by that specific DID, and the service knows it is talking to a specific device. This is better than the old models, of course, because you still retain the flexibility of rotating, revoking keys of the service, even when the device was offline or still in manufacturing, etc. Or if there was a compromise. So this is one example. Another example could be that two devices meet in the real world and they're trying to establish a communication channel between each other. Maybe they've encountered, like, device one is a Bluetooth beacon and device two has discovered that Bluetooth peripheral and is trying to establish a trusted channel between them. Almost a similar protocol can be walked through to establish that mutually trusted channel. And this is where that service discovery element is incredibly interesting. So you may discover a device over Bluetooth and the device is just broadcasting its DID, right? And so you discover that device, but you may not know how to talk to that device. And you can discover that endpoint via the DID document of that device, and then communicate with that endpoint with mutual authentication, which I think is very interesting. So on top of this very simple authentication scheme, you can build higher level services, right? So you can build, for instance, a secure software update service. You can build a mechanism where two devices can authenticate each other, but then not only authenticate, but also then go on to authorize each other. And so on this number 7 mutually authenticated channel, you could exchange some kind of authorization capability or object capability, right? And this is where I think some of the work in the DID community and the self-sovereign community is very interesting as well. Is that this notion of peer-wise unique DIDs allows us to create completely private channels. So for instance, if I have a connected light switch in my house, there's no reason that light switch should be able to figure out every time I turn the light on in my house, right? Why should they know that? There are light switch, just do the thing, right? Just turn the light on or turn it off. We've had this problem figured out for, I don't know, 100 years, right? The light switch in my house was never a spy that could report my activity in the house. But with connected devices, it can. And so how do we take back that control? On top of this notion of peer-wise unique DIDs, we could initially establish an authenticated channel using the old scheme with a public DID of the owner of the device, but then gain a object capability that we exchange with the device in a peer-wise unique manner. And then now the interactions with the device are completely private and are not subject to sort of, monitoring. And this spans across a whole bunch of devices. So I think that a lot of the work that's happening in the open web community and DID community is interesting in terms of making devices around us more private and still more reliable and secure. Because you can build these authentication and authorization schemes. And you can imagine that these authorization schemes can be more complex. So the authorization scheme, when you initially do the authentication, could say, hey, before I authorize you, I need you to prove to me that based on your web of trust and based on this specific analysis algorithm that I trust, you score beyond a threshold. So you're at least 90% trustworthy today. And if you are, then and only then you get this capability to turn on this specific light. And this is possible because that history becomes provable using things like zero knowledge proofs and data on a blockchain. And it's attributable because of verifiable credentials and DIDs themselves. So at Ockam, we're building a set of open source tools to enable all of these neat ideas from the community and make them feasible for IoT systems, make them easy to use in IoT systems. And in addition to just the ideas that we've talked about already, we're also building other pieces on top. So I briefly mentioned that we're adding support for signing cryptographic credentials via hardware modules for various different common open boards or boards that are commonly used in IoT systems. We're trying to make the protocols more battery efficient, protocols and transports more battery efficient. We're building blockchain-like clients. We're building higher level protocols like secure zero-touch onboarding, this protocol for private interactions, service discovery, signed firmware config updates, bidirectional signed data, of course, and a lot more as we go further. So coming back to sort of where I started my presentation, with all of this work combined that's happening in the SSI community, in the open web community, with easy to use tools and easy abstractions that are built on top of those very flexible sound ideas, I think we can enable a much more trustworthy and much more interoperable Internet of Things, which is very interesting and very sort of motivating to me, because I feel like that's the foundation required to build higher level systems that work to improve our lives and work to solve bigger problems like pollution and wastage and etc. So that's what Ockam is. And then I'll conclude by mentioning we've also, a few months ago, open sourced a DID parser for Go, and just because we were using DIDs. So come check out the Ockam network repo on GitHub or the Ockam DID parser if you're building for DIDs in Golang. That concludes my talk. I'm happy to take any questions. Thank you so much for listening.
Thank you so much, Mrinal. Yeah, there have been a couple of questions adding up. So let me just get started with some of them. And if anyone else has any questions, please just jump in and use the questions tool to bring up your questions. So we have Ife here, who's a regular participant of SSI Meetup. He's quick question is, what is the intention to create IoT-schema.org when we already have schema.org in itself?
That's a good point. So we haven't created IoT-schema.org. It's already exists as a fork of schema.org, but schema.org doesn't have all the capabilities you need in IoT systems. So, for example, some of the things that IoT schema has added is this general notion of a thing. It's standardizing, common IoT properties like temperature, etc. But IoT-schema.org isn't the only IoT-specific schema that's being developed. There are a lot of people doing different works. I know inside W3C, there was some work done on, I forget the name of the project. I think it's called Web of Things. But under that project, there were a bunch of schema development exercises. Their identity model and some of the other work doesn't really gel well with the IDs, but their schema is very interesting. But essentially, the short answer to your question is there are specific properties that are common in IoT systems that aren't well defined in schema.org. And that's why there are multiple projects trying to do IoT specific schemas that build on and rely on things like schema.org or Bricks schema, which is a building schema. So they use the foundational elements. So person in IoT schema is exactly the same as person in schema.org, but a temperature sensor in IoT schema is more specific.
Excellent. Another question from Ife. He's asking, what is the use case of making device passive? I couldn't understand the reasoning of the smart switch example. I remember this now. Maybe you remember.
So the idea there was, well, lots of simple gadgets around us currently are able to correlate activity, right? And the reason they're able to correlate activity is because they know who I am, right? So the moment the moment authentication is established, they know exactly who I am, and then every time I turn on or off something, the data traverses their networks, and so they know exactly who at what time turned on a specific switch, for example, right? But that isn't a requirement of that system. All I bought a switch for was to turn lights on and off and maybe do it remotely controllably, right? So what DIDs allow us to do is take back that old requirement. A light switch should just be a light switch and not a thing that can correlate my activity. So with decentralized peer-to-peer unique decentralized identifiers, we can create this private way of controlling devices, which is interesting not only in the simplistic scenario, but like lots of different enterprise scenarios that are higher level where you're trying to protect privacy and etc.
Awesome. Have a question here from Dave. Said, you described what would be called heuristic verification or authorization of DIDs. Example, you're 90% trustworthy today, so you can turn on lights. Do you know if anyone has been using these heuristic verification methods in practice yet?
No, I don't know of that. We're still building our own, but I don't know that somebody's using it. And there's a lot of active thinking. So if you're interested in a topic, drop by our GitHub. Would love to chat about this.
Awesome. Then we have a couple of questions from Drum and Read here. So let me just find the first one. Okay, what kind of customers does Ockam serve? What are the main functions they're looking at for using the IDs and SSI with IoT devices?
So maybe I can go back a couple of slides, but essentially the state of IoT currently is that most data is unsigned, right? So there's no cryptographic credentials in most IoT devices, and so most of that data is unsigned or and unencrypted, and so it's completely the state of the world is really dire. Like for a lot of IoT devices, if you can figure out the right endpoint to send the right message to, you can control those devices. For example, there was a study that came out in MIT Tech Review recently, where students at Cornell studied an ISP and measured all the industrial control traffic that was passing over that ISP, and found 97% of industrial control traffic. This is a North America ISP. 97% of it was completely unprotected and prone to tampering. So, so that's one use case, which is how do I trust the source data that I'm receiving from remote machines, and how do I trust the fact that when I send a control instruction, the control instruction cannot be manipulated. So that's one use case that is incredibly common, and very little has been done so far to implement that correctly. And then the other use cases are around, well, how do I reliably deliver firmware updates? How do I continuously manage key lifecycle and device lifecycle type of questions, etc. Right? And some of this I've touched on here, but the use cases typically fall in this notion of trusted data and control, and then trusted management of the lifecycle of the device.
Thank you. So I have 2 or 3 more questions coming here on the line. If anyone else wants to ask any questions, please just jump in. So this is a more general question. I mean, this is also from me. Like when we think about the blockchain world, I mean, like in the last 5-6 years, there's been a huge hype and pump around creating new blockchains, and some in the identity space. Like most, I mean, because I'm thinking about the slide where you showed VeriSwan and Sovereign and Ockam, and we could also add Uport and other projects, of course, where you were saying this is people oriented, this is IoT oriented. But I mean, from the way I've seen these, are they not all like generic, or you think like IoT needs a specific identity blockchain kind of infrastructure to serve its needs, or these other projects not covering that?
That's a fantastic question, Alex. So for the purposes of identity, you maybe don't need different blockchains, right? So from the point of view of identity, most of the systems are implementing DIDs. They're dealing with similar challenges and similar trade-offs. So you'll end up with roughly similar designs. But the needs of an IoT system are different in lots of ways. So for example, in blockchains are essentially distributed systems. In distributed systems, you have this essential trade-off that you have to make around sort of safety versus liveness, or consistency versus availability, right? And that trade-off, if you look at blockchains like this, let's say Bitcoin or Ethereum, Bitcoin and Ethereum have chosen to be highly available, and they've compromised consistency or safety, which means that there can be forks in those blockchains. Whereas in Ockam, we have highly prioritized consistency and safety. So what this means is that we'd rather halt the system than create an inconsistent state in the system or a fork in the system. And why is this interesting? So it's interesting if a device is a controller that, for instance, opens the, let's imagine the literal floodgates of a dam. So this state cannot be inconsistent. Otherwise, 5 minutes later, when you discover you were looking at a fork, you have no mechanism of taking back all of that water that went gushing out, right? So you need to be in a highly consistent system. So this is one example of a trade-off that you'd make for when designing an IoT system. Another example such a trade-off is scale and throughput. So what's interesting about being consistency oriented and making design decisions that favor fast finality. So for example, in our system, we achieve finality within roughly 1 second, versus say Bitcoin, which achieves probabilistic finality over several blocks, maybe somewhere between 30 minutes to an hour. And so the issue with this is that it really complicates sharding architectures. And so when you try to scale the blockchain to accommodate a very, very large number of devices and throughput, sharding becomes an incredibly complex thing to deal with. So because we anyways needed to be a highly consistent system, and we designed for fast finality using PBFT, we can support very easy sharding because all we're doing is essentially checking in at every block, and we've split the chain. And so now you can theoretically approach horizontal scalability, and you get some interesting benefits from that perspective. So I think there are lots of architectural trade-offs that will drive how different blockchains, or which use cases different blockchains are best designed for, I guess.
Okay, great, thank you. I have one question coming in here from Anand, and he's asking, are you focusing on consumer IoT market or the industrial IoT market? Each market has very different use cases and needs. Also, where do you fit autonomous vehicles, drones, cars, delivery robots, factor in your how do you factor them in your roadmap?
Yeah, that's an interesting question. So what we think of ourselves as a open source tool or set of open source tools that are solving a somewhat horizontal problem of how do you do identity provisioning and how do you do secure trusted data from those devices. And then we believe that other partners and collaborators will build systems on top that are focused specifically on industry verticals and deal with higher level industry specific use cases. So we're creating this thin, reusable, easy to integrate open source tool chain that others can build higher level domain specific systems on top of. We very much imagine that the IoT world will go where the cloud world has gone, where you don't go buy a monolithic several $1 million platform from somebody and then re-platform your entire stack. You want to specifically choose different layers in your system, and we're trying to be that one layer that provides device identity and trusted data, and then we hope others will build on top.
Great. Drummond is suggesting, hey Mrinal, have you read the DKMS design and architecture version 4 document published on March 29th? And I don't know if you've done, but if you want, I can connect you guys, because this is the decentralized key management system that Drummond has been working on. So I'll connect you if you want.
Yeah, I'd love to see the document. I think I've come across, I've certainly read the rebooting Web of Trust version of I think it's called DPKI.
Yeah,
but I don't know
that one is called DPKI. This is the DKMS that was worked on with Homeland Security, I think. Yeah, I'll connect you. So he just brought it up here. And then we have also from Drummond, as part of the Sovereign Governance Framework Working Group, there's quite a bit of interest in forming an SSI and IoT task force. Would you be interested in taking part? I'll connect you guys too, so you can talk about it. Okay.
Happy to. Yeah.
let me see what else. Yeah, Ife is asking, device lifecycle. What does that mean? Hate OAS? You know?
I'm not familiar with Hate OAS, but oh yeah, I think that's the Eclipse Foundation project. Yeah, I think that's what he's referring to. But yes, right. So devices go through a life cycle that's roughly, you know, there's and it tends to be very multi-party and very complex, right? So there's, you know, a company, let's say in San Francisco, that does the design of a product. And all they've done is design like a, you know, a schematic. This schematic goes to some production, some manufacturing company. You know, I've used some in like Illinois or China. And so they actually then source the components of the device and then start, you know, actually manufacturing the device. And there are different steps in there where they do test runs, etc. But essentially at the end, you have a produced device. And a lot of times there are disconnects even in this, right? So the devices have, the design has specs, but the components that people source maybe, you know, depend on availability as long as they meet roughly the spec, etc. So there's a lot of complexity in how this life cycle is managed. But one key part of this life cycle is at some point early on in the life of a device, you give it a cryptographic key pair if you want to trust data that originates in that device. And then and some point soon after, you give it some firmware, at least the bare minimum firmware that it can boot with and then onboard itself. So those key events are critical to establishing trust in the device in the future, right? So if you want to not have to manually reprogram devices after when they go for deployment, which is incredibly costly, you need to have tools that enable you to deal with that early process of assigning cryptographic keys to the devices and then delivering signed firmware, etc. And so a lot of companies do custom tools, and our hope is that we can build some tools ourselves and integrate into other existing tools that enable those tools to leverage DIDs directly rather than, you know, relying on the brittle PKI infrastructure, which they currently do. And there's, you know, there's a lot of like sending private keys over Excel sheets type of workflows in that world.
Fantastic. There's another one from Ife. He's asking, IoT devices are expected to operate at a greater throughput. How are we handling this in the DID case? Don't you see it decrease the output of the system because of encryption, etc.?
Yes, right. So there's a trade-off there. So throughput, I mean, blockchains, I already said, you know, we've done some work around managing the throughput in our blockchain and scaling that. But from an encryption standpoint, there's definitely a trade-off, right? So the trade-off is, do you want a piece of information that you have no way of knowing originated where you think originated? Or do you want a piece of information that you can attribute to that source device, right? And oftentimes, if the thing you're building is critical, you'd favor that attributable thing, which typically means that you either have to trade off costs, or you have to think of, you know, battery life concerns, etc. But that's definitely a trade-off. And the other scenario that I've seen a lot of companies realize after the fact is that, so they make that first choice and they say, yeah, my device is a consumer device. It's like a speaker or is a light switch or it's, you know, some thing. It doesn't need to be highly mission critical. So if somebody, you know, does something with it, it's fine, right? But that leads to really complex problems. So for example, one incident I can remember is that my past life, I worked for a smart cities IoT company. And in 2016, somebody in Dallas turned on 120 tornado sirens by crafting the right radio message. And so it became very, very loud in the middle of the night in January in 2016 in Dallas, right? So those kinds of attacks are starting to happen. And so people are becoming more and more concerned, and especially with things like Mirai botnet, which was a attack that compromised 600,000 devices that had only some variation of like 60 passwords to get into them. It compromised that and then used that sort of fleet of 600,000 devices to then go and attack the internet itself. And so in that scenario, what you want really is secure firmware updates. And to deliver secure firmware updates, you need an acknowledgement back that your firmware actually got delivered. And if you don't have cryptographic keys in the devices, then you can't get a signed acknowledgement back that says the device actually took your firmware update. So if your device is malware infected, you have no recourse back from it. So you have to sort of write off that hardware, which is why we have several tens of thousands of Mirai botnet affected devices even till today, even though that attack is now several years old. So this issue of having to program at least public keys into devices, but also private keys specific to a device into the just to manage software updates is why a lot of people are leaning into the the secure way of doing things. But then once you do that, then you might as well get secure attributable data. So the trade-offs are certainly there, but I think in a lot of use cases the better trade-off is security and reliability.
Nice. Jose is asking, do you see any interest in big tech companies to drive all the plumbing you do for their products?
Yes, there have been several efforts to do things like that, right? There are dozens of IoT platforms out in the market, right? The problem is if you just do a software-only solution and you don't cater to the device identity problem, you have no mechanism to establish identity after the fact, right? So if you've not delivered, and what ends up happening is people end up sort of cobbling together systems where they believe their system is trustworthy, but it isn't really, because the trust on first use problem is broken, right? So if the device didn't come with a cryptographic key in it, how do you deliver it a new credential in the first place and be sure that it's actually delivered? So there is a lot of interest, and there are a lot of people who've built systems in the past, but they're very monolithic, and they typically rely on PKI, and PKI itself is brittle. So I think the DID model is better, and I feel like the web of trust approach lends a much more flexible, robust answer to these problems.
Yeah. And last question here from Michael. How is Ockam in business that makes income? How will it monetize this open source project?
That's a good question. We're essentially building, so we'll operate this blockchain network and parts of this blockchain network, and that's a source of income. We're essentially building higher level products that are enterprise focused on this core open source toolchain.
Okay, awesome. And so thank you so much. I think we just went a little bit over time, but that's no problem. That's great. A lot of good questions. We have our next upcoming SSI meetup will be with Lawrence Bundy from Outlier Ventures, which will be about governance and SSI and identity. And that's coming up the 24th of April. So looking forward to see you there too. If you want to be updated about all these things, please just follow us on Twitter, sign up to the Telegram group, or sign up to the newsletter and all these other channels we have to inform you about anything you want to know. I'll be uploading this presentation and the video and the slide share that Mrinal shared with us today in the next 2 or 3 hours. Mrinal, any last final words you want to share?
No, I just want to thank everyone for coming, and thank you, Alex, for organizing this. This was wonderful.
Excellent. So thank you so much. Mrinal, I'll talk with you very soon. This was excellent to learn about machine identity. It's a big subject, and thank you everyone who joined us today. Bye-bye.